Hi, my name is Camber Guyberson. I am recording a presentation for my second Case Connections. This is part of Medical Biochem 2, the University of New England Online. So for my first part of this presentation, I'm going to address Case Connections number 2. So in case connection 2, we are looking at the MRI image and the PET scan that show a brain tumor in this patient. We can see after administration of glucose that this tumor becomes saturated with glucose, and there is a higher rate of uptake of glucose in the tumor cells themselves. So first I'm going to address this question that was posed to answer the case connection. So in a normal tissue, how is glucose uptake regulated in liver, skeletal muscle, brain, and adipose? So in extrahepatic tissues, in tissues other than the liver, sorry about that. So in tissues other than the liver, glucose is primarily regulated through hormonal and enzymatic molecules. So in these tissues outside of the liver, hexokinase is the enzyme that is primarily responsible for regulating glucose uptake. Now, this molecule has a very low Km for glucose, thus it has a high affinity. So when there is glucose circulating in the bloodstream and in the periphery of the body, it has a high affinity to begin the process of glycolysis. So it will stimulate this enzymatic cascade response. Now, hexokinase and insulin are intimately connected. So insulin is going to be the hormonal regulatory molecule that will be released by a cellular response to either activate or inhibit hexokinase. So as glucose levels increase in our body, this leads to the release of insulin, and the insulin release is going to stimulate the glycolysis response and the activation of hexokinase, the production, the phosphorylation of glucose all the way into either whichever pathway it will go to from there, like glycolysis, the TCA cycle, what have you. So I also just wanted to mention glucokinase as well as hexokinase. So glucokinase is only located in the liver, and glucokinase has a higher Km for glucose than hexokinase. So glucokinase is used as a regulatory enzyme. So when there's very high levels of glucose that are being phosphorylated by the hexokinase all around the body, the when there are very high levels, then because glucokinase has a lower affinity and a higher Km, it will likely only be activated upon a surplus of glucose. So this lower affinity allows for glucokinase to be activated when there are very high levels of glucose, thus allowing for glucose to be stored for future use, um, such as shuttling it into the pathway of formulating or forming glycogen, and um, and also shuttling glucose to these extrahepatic tissues where it's needed most. So now that we've talked about glucose in the rest of the cell, um, or sorry, the rest of the body rather, I will go back and reference this image. So we can see from this image that glucose is rapidly saturated in these tumor cells. So this would indicate a modification of these tumor cells to have an even higher affinity for glucose than other cells of the brain. And possible modifications could be a change or a deregulation of hexokinase. So this could even maybe increase its affinity and lower its Km even further, so that these tumor cells are rapidly saturated and have an extremely higher affinity than other cells in the brain. Um, so some type of modification that caused a rapid glucose uptake would result in glucose being saturated in these tumor cells, which would allow these tumor cells to have a really high energy supply. So this is what allows these tumor cells to rapidly grow, because they're using this glucose to generate ATP and to facilitate the rapid growth of these tumor cells. Okay, now I'm talking too much. I've got 4 minutes left. I'd like to touch on case 4. So case 4 is in relation to galactosemia. So I believe galactosemia is the correct answer to this question. Given that this is an infant who is primarily ingesting breast milk, this points to galactosemia over fructose intolerance, which can have similar symptoms. And a lot of these symptoms are consistent with galactosemia. So galactose is broken down from lactose that is in breast milk. And those with galactosemia have difficulty processing or breaking down galactose, and it can cause very serious health issues, including enlargement of the liver, vomiting, um, just general intolerance to lactose or breast milk or any type of milk in general. So one thing we can see with this patient in case 4 is the measurably larger liver. So this is directly consistent with a diagnosis of galactosemia. Um, Additionally, other symptoms congruent with this case would be the recent development of symptoms. So sometimes those with galactosemia, they don't develop symptoms right away upon ingesting breast milk, though some do, and sometimes it takes a few weeks, which would be consistent with this just 8-week-old baby developing these intense symptoms of galactosemia. Um, so I just wanted to answer this question that is proposed here. Epinephrine is administered and there's no increase in blood glucose, but an increase in blood lactate. So if this baby is having trouble processing lactose to produce the proper sugars, then it could be inferred that gluconeogenesis is happening at a higher than normal rate in this infant. And this would explain why there is an increase in blood lactate in this child after epinephrine is administered. So I'm gonna go through these answers as to why I do not think it is C and D. So I've touched on hereditary fructose intolerance. Um, Glycogen storage disease would not be indicative of being intolerant to breast milk. So that would cancel that option out. And the glucose 6-phosphate dehydrogenase deficiency, this would present symptoms this would present the death of red blood cells. So this is a pretty different disorder, and it would not be presenting this enlarged liver or other symptoms we're seeing in galactosemia. So that is why I have chosen galactosemia for this case 4. And that is all for this presentation. Thank you so much for listening, and thank you.